different methods which is available. Along with that, what are the basics data inputs which is needs to be provided for network analysis. And along with that, we'll also see that how you can execute that in QGIS and other open source software, along with the few basics algorithms which is being executed in those softwares. So let's start with the first definitions. So before going in detail, let's understand that why do we do a network analysis. So if you are aware of the navigation systems, especially the systems which is being used by in form of Google Maps, which we are currently using quite widely, but later on there is also an expectation that we are going to have intelligence systems, means like intelligent network systems, where there will be need of additional services which can be integrated to your autonomous vehicle navigation systems and all, and then the navigations can be done without the intervention of the human beings. So from that perspective, we will see that what are the basic services which is currently available. So we can just categorize these services in two major group. One is called map-based services. So basically under this services, what happens is basic objective is to whatever processing or analysis your GIS software component is going to do, they are going to provide you a map, and that maps can be used for navigating in different locations. For example, if you use a map in Google Map, so you provide start and end locations, and you get different paths. So how you're going to follow the paths, then you can do a route planning accordingly, and those kind of analysis can be carried out under the map basic services. So and all these generally is being used it basically uses the cost-based estimations techniques, which one of them is the shortest path route. So most of the time we use only the path which is shortest in nature. That is, we would like to know what is the shortest distance. We should get a path which is the shortest distance between 2 points. But sometimes it may be that the distance may be a shortest one, but the time taken might be a larger one, and so on. So in those cases, we need to do a certain modifications. There are a few specialized map services also, which provides you these kind of maps. For example, if they will tell you that nowadays we are having a electric vehicle is quite widely used. So there are now services which talks about that which particular road, if you follow, the kilowatt per kilometer ratings will be lowest. So that may be a longest path, but your cost of running vehicle will be lesser. Same thing can be also be done with the help of petrol and other vehicles which can be used for, which can also use the similar kind of services. And then all these services basically is that you get a path, and then the path is being displayed in form of maps, and then you take a decision on the basis of that. The other navigation systems, which is generally called a location. So if you want to just know where you are currently, so in those cases you get a latitude and longitude computed using your mobile devices, and that latitude longitude can be placed in already georeference maps, so that you can come to know where you are. So that's one systems where you can use them as a map services. There are also other services where you just give the latitude and longitude, and you can get a textual output which can be then integrated to different systems to give the detail of the path. For example, you may be interested in what are the different intermediate path which is being followed by a vehicle, or a particular fleet which you may be owning. So in that case, the latitude longitude will not be a good way of representation how the different vehicle has traveled from start point to end point. The reason is those will be only numbers. So from the user point of view or the human point of view, that is not very useful. So in that case, you need some kind of services where you just put the latitude or longitude and you'll get the address back. So you'll be able to get the address back, and that can be represented. So those kind of services are there, which is, we call it as geocoded addresses. Same thing also can be done in the reverse geocoded cases, where you just provide latitude, longitude, and corresponding place or names can be provided. So both the services comes under the location based services. Then there are also directory based services. For example, if you are at any place, you may be interested that which is the nearest clinic, or where are the taxi stand which is available. So this, which is quite helpful for the people going in any unknown places, and they can get a lot of these information. So those are called directory searches. And of course, the location based services can also include the routes, which is basically finding out the shortest path to some destination based on your current location. For example, you may be interested that which is the nearest hotel or from the current location. So such kind of queries can also be carried out. The important point over here we should observe is that all of these location based services requires the current, most of them will be requiring the current location by default, but you or you may also provide that any latitude or longitude to get the service output. And the output of these can be in form of map, or it can be a textual documents and so on, which can be consumed by human or maybe different systems. So all these navigation systems works on using basic data structures or basic systems called networks. So let's see what is the meaning of network. So generally, whenever we talk about in GIS, the networks basically is nothing but a set of connected nodes with the edges. So it means you'll be having a certain points, and each points will be connected through the edges. So that's the first or simplest network. So similar kind of definitions also exist in computer networks and utility networks and so on. So it means there can be a multiple applications, but the idea of representation of the networks is same, that it is going to have certain points, and those points are connected through edges. Then network can also be a planar or non-planar. So this is very unique in terms of navigation systems, because certain networks can be non-planar. What it means is that you may be having routes or edges which may cross each other without having any connecting point. So if that is the case, then those are called a non-planar and planar networks. We'll see also a few examples of them at later stages. Then these networks can also have basically based on the edges, where we can say that the flow of material or informations is going to happen only in one direction or both the directions. So accordingly, you can have a networks which is a unidirected or basically a directed one. So undirected or directed generally also called the bidirected networks. It means that in both the directions the material or informations can flow. Then each of these networks, when you build nodes and points, then you'll be having a certain structures. What are those structures? We'll just see at later stages. But just for a brief stop over here, in that case, structure basically talks about that how does the networks looks like. So is it a kind of a single line connecting all the points, or there are multiple lines? So that on the basis of that, we can define a lot of different characteristics of network, which is quite useful for defining or giving the network failure ability or network capability to handle the different failures and so on. So few of such examples which are there, network is like the transport networks or the navigation networks. Then there are utility networks, which is basically the sewerage line or water supply line, which is basically connected. Those are also a kind of example networks, and they are being used for managing the different transport systems or utility network analysis that can be carried out on these networks. So these networks are being used for carrying out certain network analysis. So generally, what is the meaning of network analysis? If somebody wants to know, so you have to think of that network analysis basically, or generally, we are over here we are talking about the transport-based network systems. So where we are mostly interested in finding out the optimal path, or the path which is least under the cost. So there are a lot of different problems associated with that. Those are called travel route directions. So it means like you may be interested that if you want to travel, let's say 5 places or 6 places, so what should be the order of the travel of that path, so that you have to cover a minimum distances. So those kind of problems can be solved. Then there are also certain network analysis where you do a kind of partitioning of your network. So what it means is that you take a network and you segregate or break down into small pieces, and these pieces talks about or each of those pieces may be following the certain conditions. So that can be categorized. The example of that may be that, for example, you may be saying that I want to see all the areas which can be traveled in within the 10 minutes of distances. So in that case, you will be seeing that what are the different road networks, or what are the different segments of the road which can be reached from a particular point. So these kind of network partitioning becomes very useful in the cases where if you want to define certain catchment area, or finding out the service area based on placement of some service center. For example, if you want to set a shop and you would like to know that if somebody requests that he wants to have certain services from that shop, and what is the minimum time guarantee which you can provide to them. So that can be, on the basis of that, the area can be partitioned, and you will be able to say, okay, these many areas you can travel it within 10 minutes and so on. So those are actually the network partitioning, where your network just gets broken down into two or more number of basically pieces which has no component common in that's the basic criteria which has to be followed out. Then finding the closest facilities and routing problems are there. Sometimes we also do a certain network structure analysis. So network structure analysis is that if, let's say, if one particular bridge is off, then what will be the overall impact of traffic flow? Will it going to impact the internal traffic system as well, or not? So those kind of analysis can be carried out based on the structural analysis under the network analysis component. So all of these network analysis, whenever we want to use it for utility and other systems, so we have to define or understand that what are the different characteristics of these networks. So if earlier I said that each of these network is just connected edge and point, so which are called network components, or a similar first level of components. Then you have a structure which is basically talks about the construction. So do you have multiple connectivity points from one locations to the another locations, and so on. So those kind of characteristic of network is falls under the structural component of networks. And then each of the edges may be having a certain cost associated with that. So those costs may be each of the edges as a single point, or there may be a cost associated with as a group, or you can call it as a zone specific cost may also be associated with that. So using that, we can do and carry out analysis like how what is the best way of transporting certain goods in a networks, and such analysis you can do it in vector datasets as well as raster datasets. So there might be a few questions that how come the raster is going to be used for network analysis. So in the rasters, generally, as you may be aware, that raster is nothing but consists of a set of grid of cells, and these cells have a very unique structure. So means each of the cells position relative to other is quite fixed, and that can be used for network analysis. And this is quite widely used to find out like basically a catchment area for a river, or maybe just delineation of different flow of materials which is going to happen in on earth. So those kind of analysis, which is where the raster data sets are there also you can carry out the network analysis. So if you see the lists of the such network analysis, so which is related to a transport problem, is being shown in this case. So as you can see, the first part is basically a vehicle routing, which says that if you want to start from location of starting point and ending point, and between there are a few places which needs to be navigated. So what's the best places? So those are like starting and ending point are there, and in between you have to travel the certain places. So that's the first example of the routing. Then there are very specific routing problems. So these are basically the cases where, or people who may be using in logistic basically anyone who is using the logistic networks, so they will be using such vehicle routing problems. So these vehicle routing problems basically generates a set of paths which from starting point or the starting depot, you can travel multiple places and you can come back servicing all the different clients. So in this case, there might be a certain constraint. For example, there may be a capacity of vehicles. So it means that you may be having a small truck which has a certain fixed capacities, and based on those capacities, each of those different points which needs to be traveled will be having a different amount of materials which needs to be delivered. So accordingly, you have to find out mapping or considering all these different constraints. You should be able to find out or do a fleet management routing plan. You should be able to generate so that the fuel and other or maybe the time which is required can be less, or maybe fuel consumption will be low, and so on. So those kind of optimizations problems can come under the vehicle routing problems. Then the traffic analysis, which is quite you are aware of that. If you see on the certain areas which can be highlighted and which can say that which particular area is having a kind of higher traffic density compared to the other areas, and so on. Then there are also a closest facilities which is given a point, like in that case you just provide a point, and you need to see which are the different places which can be reached within certain amount of constraint, like certain within 10 minutes, 5 minutes, or sometime you may be interested that from that location you want to find out all the different places which is present in a city, and so on. Then the other application which is basically is used called location and allocations, and this is also true for raster based analysis as well. So in this case, what happens is locations, maybe a raster or a vectors, we'd like to know a kind of catchment area. What in that case, what we would like to see is that what is the path or what are the different places on a surface which you can reach from a particular point. So those are the location and allocations examples of the problems which we can deal with. Then there are service area mapping. So in this case, you just provide a certain constraint. Like in this case, this map can represent that what are the different places which you can reach in 5 minutes, 10 minutes, 15 minutes, and so on. So this gives you a kind of buffering. So you till now you might be already aware of that in a vector there's something called buffer, which is just gives you the radial distances. But in this case, it gives you the actual on ground distances which person needs to travel on a road. So certain roads may be having a bending, so it means that path length will be quite higher. Even if you see the radiant displacement will be quite lesser, but distances wise that could be a quite larger one. So in such cases, it gives you a kind of partitions or the areas of a particular network. So, and this also helps us to do a kind of service checking. For example, some company may claim that they are able to reach to any places in a city within 10 minutes. So it means that if you know their locations and you know the average traffic basically speed on your networks, then you can easily tell or claim tell or find out that that claim is correct or not. So in those cases, service areas can be identified. You can also find from the service area gaps, like if somebody is claiming to have certain services to be delivered in 10 minutes, but if certain portion are being left out, which is beyond 10 minutes, so in those cases you can look for a new centers that can be created. So this basically helps you identify those gaps. Then there are also extension of multipath distance, which is called a kind of cost estimations analysis. Then there might be a different path level analysis which we can use. So all these problems are quite important from the network, especially the transport network point of view. So let's see the few examples of different type of networks. So networks can be directed or undirected. So means there is only a single path. So for example, the river flow network, or the network which basically any river is going to, or the different tributaries of rivers is going to constitute a network of different drainage. So in that case, what happens is that the flow of water is going to occur only in one direction. So from the higher potential or higher height to the lower height, that's generally the flow expected in any natural course of river flow. So in that case, we can say this particular path or network of different streams is a unidirectional, or it flows only in a single directions. But if you just come to cases of let's say for different road network, so in that case traffic may be in one direction, or it can also be in both the directions. So accordingly you'll be having two different type of directed and undirected networks. Apart from that, your networks can also have multiple levels. So it means that you may be having network at the bottom, and on the top you may be having a flyover, which is the another connectivity provided from one point to the another point. So in this case, your network will have a multi-level presentations, and accordingly those conditions has to be used. So those are actually non-planar networks that needs to be considered. So generally these are basically a part of navigation systems where such kind of networks can come in. So as networks is consist of a set of nodes and lines, these node and lines can also be based on that you can define certain network structure parameters. For example, if you are having all these point which is being connected using edges, and these edges can represent a particular path. So based on that, you can define that is the network is centrifugal or centripetal. What it means is that is the all the traffic flows from outer ring to inner ring. So in those cases, you can say it's basically a centripetal flow. Similarly, there may be a traffic flow from inner ring to the outer ring and so on. So that gives the characteristic that if you are able to handle or manage the network flow at the bottleneck or at the centers, then probably you will be able to manage the whole networks across. So that's basically the characteristic which can be used. Similarly, the network can be a single line point of failure. For example, in the centralized network, all of the different points are connected to a center points. So if any failure happens at that junctions, there won't be any connectivity left. So it means all the points will be a kind of isolated one. So there will be complete disruptions to the networks. Then there can be a hierarchical structure. So what it means is that which is generally a part of decentralized network. So you may be having multiple zones. Basically, for example, you may be having 3 or 4 different residential zone. All of those residential zones are then having a feeder line or feeder roads which gets connected to a central junctions, and then that can go and the traffic can flow from there to the different offices, areas, and so on. So this gives you a kind of example of decentralized networks and so on. In some cases, there might be a full connectivity. So even though your network may be distributed, and in that case, network may be having internal structures. So it allows the multiple paths to be followed. So accordingly, your network is quite resilient. So if there is a high traffic in a particular directions or a row, or a particular road, you can look for you can just assign a new path from one locations to the another locations. Then you may be having a networks which provides you full connectivity from point to point, or there may be a hub and spoke networks, means from different locations all the materials will get collected at a one point, which is called hub, and from there it will get distributed to the other side. So generally in the logistic networks or e-commerce industry uses hub and spoke network. So it just does a kind of balancing between point to point connectivity, which is requires a high cost as the number of connectivity increases. So the cost of new building of new networks road is also goes higher. So the hub and spoke basically requires a kind of buffering systems, where at the hub you need to have a certain storage capacity built in, and there the materials can flow from different points, can be stored for certain durations, and then can be forwarded further. So it's a kind of compromise of the higher cost of network connectivity. So these network structures, when you have such kind of connectivities representation in form of point and nodes, then we can carry out the analysis like, is my network is having a single point failure, or what is the total resilience, can my network follow multiple failure, multiple point failure, and so on. So those kind of things can be analysis can be carried out. And these structures also also is important to define a cost. So for example, if you take a transportation cost, maybe in term of distances, or it may be in term of fuel cost, or maybe a per kilometer rate of transportation, and so on. So those costs gets affected on the basis of the parameters. So those parameters related to those costs can be affected due to the structures of the network. So if the network is having one-to-one connectivity or multiple connectivities, then there might be a different amount of cost which may be associated with that, and that may help to find out the different bottlenecks areas and so on. So it means that it can provides you the conditions under which the operations are related to network analysis gets carried out. There are also additional structure modeling we can do it. For example, you may be able to do a partitioning and orientations analysis. So that's basically used in a cases where you may be interested in that how a particular city is growing. So is the growth is happening in northwest directions and so on. So in those cases, the third, or generally we call it that a higher level of information instructions, where you want to just do an analysis that how a network is evolving with the time and so on. And then you can look for what's the reason behind it. So is it like the new development which is happening, or what are the causes that network is only flowing or growing in a particular directions. Then there are a lot of other representations. So those are basically representations and so on, like it may be a concrete or abstract level representation. So all these actually different type of networks falls under the topological network analysis, and they basically affects the this gets affected, or the important parameters to do such kind of structure modeling and analysis is what's the length, directions, connectivity, and so on. So accordingly, the patterns can be identified for network modeling. So let's see that once we understand the different potential of networks and what we can do with such a network data sets, let's start it with a few basic operations which we can carry out on such networks. So before going that, we have to first find out, like, is the path, whatever path or distances which you want to find out, is it the network is going to be in ordered or unordered way. So that's what you can do. You can find out based on the least cost path between 2 points or a multiple points and so on. For example, there may be cases that from one origin point you would like to know what is the distance it will take to reach multiple locations. For example, there might be a manufacturing units, and you would like to know if certain perishable goods which is going to last, let's say, 1 and 2 days. So you'd like to know within 1 and 2 days what are the different locations which can be served from the manufacturing unit. So in that case, we need to know all the paths in the network from origin to the all the other locations which is reachable, and so on. So this, in that case, we can additionally use, apart from the locations, the geometrical and attribute data sets can also be applied, so that the cost based analysis can be carried out. And the certain or the other categories, one important point over here we have to understand is that whenever we say the path has to be ordered, so it means like it will be a kind of set of nodes or location which has to be followed in a sequence. That sequence has to be maintained. Then we call it an ordered path, optimal path finding. If there's no orderliness, then if there's an order is not particular, there's no particular order. So means you want to go from A to B, and in between there might be a multiple places which you want to visit. If your order is not important, then the pathfinding will be following one particular optimization algorithm. If the order becomes an important, then in those cases the other optimization algorithms can help you to find out these problems. In fact, these are very important, on which the lot of services are also being built. For example, you may be interested that you want to travel from one place to another locations, or there may be 2 and 3 days trip for different visitors, or to any city. So in that case, there might be certain requirement. For example, if a tourist is having certain kids, so they may be interested that one day at max they can travel only 4 hours, or in a maximum sitting they can travel for 2 hours or 3 hours. Then in between they need around half an hour break, and then they can continue their services. So maximum such kind of additional constraints can be put, and on the basis of the different optimal path findings can be carried out. So all these constraints, along with the order in which the different location needs to be traveled, we can find out the effective cost paths, or the network path, and which can be quite useful to the different type of users. In fact, there are a few web services which provides these kind of functionality, and they charge for it. So it means like it's also a kind of revenue source generation, which is not possible in your Google Maps and so on. Then there are the cases where network partitions can be done. So those are actually allocation and trace analysis actually falls under that category. So it's basically defines based on the criteria defined, like you can say within 10 minutes travels, or 10 kilometers, or what are the location which can be reached from one locations to the at a distance of 10 kilometer and so on. So those kind of things can also be carried out. So these two are basically two major transport based network operations which we see currently being used in the GIS domain. The network analysis is being quite widely used in network systems, where your network can be consist of multiple connectivity components, and there might be a multiple services. For example, your network structures can be consist of a road network, a line, a rail networks, or maybe a ship connectivity, and so on. So based on that, the complete general transport structures can be built in, and accordingly the network analysis can be carried out in such a complex network structures, which gives you a kind of guaranteed or a kind of minimum or maximum time which any kind of flow is going to happen in this network. So that helps us to do some kind of optimizations in the at the operational units of different organizations. So let's take a few example of network analysis which we can do it. That's basically optimal path finding. That's the first example. So in this case, you need to find the most efficient travel route path. And in that case, connectivity is very important. So even though physically it may look like that there is a two nodes just a few centimeter apart on your data set, but there's no physical connectivity between them. So in that cases, the network is not going to consider the connectivity component, and the path may be quite higher. So it means that network connectivity or the topological structures of your network has to be very important. Then apart from that, since this is an optimization problem, so always in any kind of optimization problem, it will be a kind of or requirement will be that you have to provide some kind of cost function which is going to take an input, and that will give you the then that cost function needs to be optimized so that your overall cost should be minimum or maximum, and so on. So those kind of cost functions can be defined on the top of that, and these basically helps to find out a lot of problems related to all those network partitioning, traveling salesman's problems, and so on. So those kind of problems falls under that category. To do that, these analysis in GIS, what you have to do is any kind of transport networks, you have to convert them into a network data sets. So you may be having GIS layers that may be a monomodal or bimodal or multimodal. So monomodal means that you may be having a road networks only available, and or you may be having a multimodal. So means your network maybe consists of a certain one layer as a road, another layer maybe as an rail networks, and so on. So these GIS data, what you have to do is you have to convert them into network data sets. So as I was telling, that network data set is consist of node and edges. We'll see that how this gets represented at later stages. And then once you have this network data set available to you, then only you can carry out the network analysis. So there are multiple ways of creating this network data sets, like in certain proprietary software, for example, ArcGIS, they provides the provisions where given a set of GIS datasets, you just select them and you can convert directly into network dataset as a part of your geo databases. In some other open source software like QGIS and so on, what they do is they take all these datasets during runtime, so during executions, and at the runtime or executions time, they create a new network datasets which can be used for analysis. There are certain open source databases also available, for example, PG routes and so on. So those kind of geospatial network database extension can also help you in creating these network datasets and then carrying out the analysis. So generally, whenever you want to carry out those analysis, you have to do some kind of modeling of your spatial modeling of your data sets. So we call it basically conceptual or logical model and physical data models creations. So the creation of databases or the network data set is an example of a kind of physical data model. Conceptually, your models may be road networks and so on, which is coming from the GIS datasets. But apart from that, there may be a logical connectivities and so on, which will be consist of different attributes, which can get generated during the operations during that time, the additional attributes can be added to those relationships. So these are the few examples of network data sets. So like you may be having, if you want to do some kind of analysis, and if you're a first time users, so you may be interested where you can get all these network data sets. So there are few openly available network data sets, like you can use OpenStreetMaps or OSM maps. There are air traffic data sets which can be created or which is available. Then in some cases, there are also web services, like if you can give starting point and ending point. and between whatever the path is there, that particular path will get created and will be made available to the consuming services. So all of these data sets, when you create, you have to make sure that these data sets should also have, apart from that geometrical connectivity, like continuity and their locations and other parameters are present. Apart from that, you may be also interested that is there any special cohesion is there or not within that, or there's a topological connectivity is existing in those networks, and so on. So once you have these two data sets available, so you can carry out the different level of analysis. Like you can carry out the shortest path distance analysis, where we just need to have a connectivity. But if you are interested in finding out vulnerability or the hierarchy, trying to find out what are the different hierarchical structures which is present in your network and so on, so those kind of things you can do it only when you're having a complete network dataset structures available to you. So now let's see that how the actually the GIS data basically is there, which gets converted or which gets represented in your basically as a network datasets. So in this is just an example where you are having a locations, and this is connected to a multiple road networks. So those road networks are basically streets and so on. And then you'll be having all these road networks will have a certain intersections, and each roads may be having a multiple segment. So it means like on ground or conceptually there may be a one road networks or one road may be there, but it may have a lot of bends and so on, which will get converted or which will get created due to road segments, intermediate road segments, and so on. So these models along these components along with the turns actually provides the definition of your network datasets, and then you can add a certain structure related to on each node, is the turn is allowed or not, or what is the turning cost. Like if you travel in a straight road, there will be one cost, but at the junction points there may be a cost. Even though if it is just a bending, the traffic will get slowed down due to the reduction in the speed at a bending locations. So simply in the, if you talk about a kind of math model, so it's basically consists of vertices and edges which gets created. For example, this is just an example where different junctions and roads are there, and their connectivity and flow of direction is being represented, which can be represented as a part of the node graph. For example, over here there are total 9 vertices, so from starting from node 1 to node 9, and in between there's a connectivity, so those are called the edges. So edges can be represents the starting and ending point of each nodes that can be there. For example, edge can be represented as an N1 and N4, which basically gives you the connection on the leftmost or the west point to the in the direction of the northeast direction. So that's the first edge which we see it. So those kind of edges can be created from these graph models. So you can try to create a kind of network on edges at your side based on which will give you a kind of representations as we see at the middle. So now let's see a few example of network analysis which is being used. Before that, we have to understand that if you want to do these analysis programmatically or using your own method, which is not available in a GIS software, but you want to build your own method and so on. So for that, you need to know a basic representation of your network. So one is called, the network can be represented as a basically as a part of an array. So where the connectivity can be represented as an entry in row and column. So on the row and the columns can be you can create a matrix where rows and columns will represent the nodes, and in a particular row comma column the entry will represent that is there a connectivity existing between any node and not. For example, if you take the on the first figure, there's a connectivity between point 1 and 2, and from 1 there is no connectivity to either node 3, 4 and 5. So as you can see in the first row, which is the first node, and it is connected to node 2. So there is a entry at the node 2 at this point, or in the second column of the this matrix. The rest all of them are actually having a zero entry. So this is basically provides a kind of connectivity graph, or connectivity representations can be put in. So this can also be modified separately, and these matrices can help you compute the lot of different relationship mathematically. For example, you want to find out what are the places which is, if you started from the node 1 and you want to find out all the places which you can reach it in 2 hops. So means that you want to go from node 1 to any places at 2 hop distance. So in between you can just land on any node and go forward. So what are the different location which you or what are the different nodes which you can reach it? So those kind of computations can easily be done with the matrix representations, and it's possible to do so those analysis directly in your data sets. Then there are also other representations like linked list and so on, that for the directions you can just provide two edges. So each of them will be representing only a direction in one. So you can have a connectivity and edges represented for data sets. Then for each of these networks, you can define certain network structures, parameters, which are quite useful for transportation analysis. For example, there's a one index called detour indexes. So this basically gives you the kind of network properties which talks about that if there's a distance and shortest distance and the total distance. So that basically gives you the worst case scenario which you can get, or this can also give you representations that how many different paths on an average exist between 2 points if you start from one locations to the another locations. Then there are certain other indexes like pi indexes, which talks about the longest path and the ratio between the longest path and the shortest path. So that also talks about the resilient or the relationship resilient of your networks. That is your network is having multiple connectivity or a single connectivities. So those you can find out. For example, if pi index is just 1, so it means that your network is having a less resilience, because from any location, if you go from point 1 to any points, there is only a single path exists. So that is easy for finding out a bespoke or structures, but in reality you may be having a mix of structure networks components, where certain network components may be connected, certain networks may not have connectivity, and so on. So if you'd like to know what is the actual status of road network in a particular city, for example, if somebody wants to do an analysis that how is the different cities networks, or which particular city is having a very good network connectivities, even if there are certain failures, still there won't be effect on any traffic. So if you want to do it, so such kind of analysis or at the structural levels, then you can use the pi indices and so on. So there are a lot of other indices which is available, and that you can have a look during the analysis. So just to give you an example how the such kind of structural analysis can give the idea about the networks. So on the left hand side you can see that there's an average path length which is there on the x-axis. You can see there's a network length that can be computed. So based on that, if you just draw a graph, so these graphs basically gives you that if your network is having a single point failure, where you may be having average length path or average length paths to be quite higher, and the network length are quite, or average length of the network is quite low. So it's basically taking the total length of the network divided by the nodes. So if you compute that, so that basically gives you the network length, and average path is basically the path which is existing between two nodes. So if you draw these two data points in a graph form, so that can give you an idea about the structures of a network. So is it your fully connected, where your networks is? So is it like fully connected network, or is it there's only a single point of failure? So in between, if like for example the network of type B and C basically falls somewhere in between, so it means that there is a connectivities as good connectivities as well as the average distances which needs to travel from one locations to another locations are also good in these cases. So this becomes an important for structural analysis point of view, network structural analysis point of view. Along with that, it is also becomes an important uh, part to understand what may be the estimation of the costs, because sometimes there may be a need, or someone may say that okay, we need to make this network of a particular city in a better way so that it can be used for manufacturing hub and so on. So in those cases you have to give a kind of expected network structures which will be sufficient to is somewhere in between having a good length and as well as average length, or as well as the network length. Both of them should be quite optimally good in those cases, because as you add new roads there are additional costs will be there, so you have to provide an optimal cost for planning purposes and so on. Then you may be using for partitioning, like on the bottom you can see that you can find out the path location from starting point to end point, where there might be a multiple path, but in between you'll be having different differences in elevations. So as there's a differences in elevation, so you can understand that if your vehicle route is, or a vehicle route is having, or any kind of vehicle which is dependent on slope, like if you're going uphill and downhills, so there may be a differentiation different cost for per kilometer running. So you can just select the path which is based on this to find out the best path. So that path may be a slightly longest, but it can be traveling only on the flat terrain or a mix of uphills and downhills. So accordingly the overall cost of the travels can be used. So these kind of different cost metrics basically helps you in computing such details. So let's take a few example of single shortest paths and so on. So one of them is basically is being used by using algorithm called Dijkstra's algorithm. So as I was telling that these basically the network analysis, the basic mm, theory is that you have to have certain amount of cost optimizations, and that's what you have to carry out. So you can follow multiple approaches, like you can use the greedy algorithms, brute force algorithms and so on. So there are multiple ways of computing it depending upon your cost of computations, and each of those are basically going to take an input to the graph and output may be generated. So just an example of that, you're having starting point and ending point. Let's say you want to go from location A and you want to find out the total path length if you travel to all the nodes B, C, D, E. So for that you can just take a just a kind of initial example which is quite and these examples are also available in different platforms, quite animated platforms. These examples are also available which you can explore it, but I just want to go through and show you that how it works. So you just note down all the nodes which needs to be traveled. You just put a cost where you're starting. So in this case a point A is there, then you start looking for the path which is going to be of least cost. So these costs generally means maybe in smallest time which you can travel, or there may be a distances and so on. So like in this case from A you can possibly go to location B and C, where the least cost of in both the location is that it is reaching to C will be a least one. So what you can do, you can just include the C as the first entry point and you can just travel from point A to C. Then from C what you can do is you can look for another connectivities in the non-reachable nodes. So from the C the nodes are already being the A has already been covered earlier, so we need not have to go back to again A. Look for another places which can be reached from A and C in a least cost. So that's what we do it, and we find out from the C we can reach it E D of E D basically BDE with a cost of 711 and 5 unit. So out of these the small amount is smallest of them is 5. So we just include E as the next input. Then again, from these three nodes, we start looking for the total cost, which we can reach it or which we can follow from different locations. So accordingly, there are between B and D, the total cost is length or the cost will be actually 7 or 11. Sort of that B is the least one. So it is selected, and same way the D is being covered. So this gives the kind of sequence of the nodes. So which I was talking about at the beginning. So generally the sequencing of these nodes in a particular order becomes an important aspect in a lot of optimizations techniques. And these optimization techniques put all these algorithms basically constraints require certain amount of constraints to compute or make these sequences in order. Then there are also example of that is basically spanning tree algorithms, which basically takes the starting and ending point based on the minimum cost from all considering all the paths. So it basically considers all the paths. So this is again it can be computed using Prim's algorithms. You can find out more in detail after this class. So all these algorithms basically executes can be executed in GIS software. So generally, this just gives you the different basically different processing components or which is available in your processing toolbox of QGIS, where you can carry out service area analysis and as well as shortest path analysis. Shortest path analysis is generally point to point. So any things which you see point to layer or point to point, so those kind of analysis is shortest path analysis, which actually follows a kind of algorithm, Dijkstra's or the Prim's algorithms. Then same thing can be extended to find out the service areas, which is nothing but a network partitioning techniques that can be viewed. So those are the other analysis tools which you can carry out on a QGIS software environment. So with this, actually, I'm just going to end the current sessions. चलो. Okay, so as a part of the interaction sessions, there is a questions related. The question is, can we merge two or more data models? So I hope that basically you mean to say that there are physical and other data models are there. So if you mean to say that we can merge those two physical as well as logical models, so that is not possible. Those are basically a kind of cases where we do a kind of data organization. So those models cannot be merged. But if you mean to say that data models related to different network data models which we have discussed, in that case we can merge the output of one model based output with the another model based output. So that can be done. But in term of logical, physical, so those are basically a kind of models which is just for understanding the way you create a different flow graph and then or maybe methodology chart, and then finally you implement it with the programming and other modules. So in those cases, these two things has to be cascaded. Similarly, there are physical model, there are logical models. So those are a kind of conceptual and as well as database related models. So though the database related models or physical models are a kind of implementation of the physical based models are actually implementation of the logical model. So in that sense, it cannot be merged. So this question is not very clear, but I hope I tried to give the answer in both the cases. The other question is related to can explain the usefulness of superimpositions theorem in linear network. I think we haven't discussed superpositions theorems in these lectures. But if you want to use them, then there has to be a kind of linear algebra based systems that has to be executed. Then there has to be a lot of other constraint needs to be put in, and then finally you can integrate it. So currently we didn't discuss about the any kind of superimposition or linear network theorems or the computations parts. We just discussed only the basic measures, how to derive the different measures. That's what we have discussed, and as well as we try to understand how in the geospatial domain the different network data sets are actually preserved inside, and then which can be used for the computational part. And if somebody wants to design or create a network based analysis, so what are the important factors or what are the ways to go from requirement to finally implementations in a logical or physical levels? That's we discussed. So we haven't discussed anything related to computations or algorithms much more detail except one Dijkstra's algorithm, just to give you an overview of one algorithm has been discussed, but computational things has not been discussed, so that can be taken sometime at later part. But if you think that you need to use this linear network superimpositions theorem, then in those cases you can use little bit of algebra based systems. That can be done with the help of taking these geospatial road networks can be combined, and then that can be taken into considerations. I think if there's no questions, we can yeah, I think if there's no more questions, so I think we can break for the sessions. Have a good day. Bye.